Hi, everybody. So welcome again to reInvent. Happy to be here. My name is Yaniv Donnenfeld. I'm a business development manager for container services at AWS. And we're in CON301, Mastering Kubernetes on AWS. So we're going to split this session to two parts. One is going to be the Mastering Kubernetes on AWS, which will talk about Kubernetes in general and give you some tips and best practices and how some aspects of Kubernetes like networking and security looks like. And then we're going to have Carl Adamo from Snap, who's going to talk to you about Snap and their journey through Kubernetes in general and what they do on the platform. So this is a rough idea of the agenda for the day. Just kidding. Yeah, so we're going to talk about Kubernetes. And when it comes to talk about Kubernetes, when you start off building your workloads on containers, and I'm pretty sure a lot of you know this, it's really, oh, one more thing I forgot, sorry. The breakout repeat, that's today. So that deck is done. OK, so when starting to talk about the local development, that's easy. That's usually just relying on Docker or just running a simple Kubernetes cluster either on your laptop through things like Minikube or just running them in the cloud in a very simple way. However, when it comes to running things at scale, that's when things become more complicated. So talking about separation between control plane and the data plane. Control plane is all the Kubernetes components like masters, etcd, in which by themselves run a few components on the master like the controllers, the API server, DNS, and a bunch of other things that are required for the cluster to function correctly. And then you have your worker nodes. These are your EC2 instances on AWS, on which you're going to run your Docker containers. And then that poses a set of challenges on its own, because now you have to kind of scale your workload on top of a lot of instances, which are spread across multiple AZs, and you have to figure out things like how to schedule them properly on your platform, how to connect monitoring and logging and tracing, debugging, and generally speaking, managing that fleet, which is an operational burden by its own. So those are like two different challenges, and we'll talk about those two aspects. So starting with the control plane, and I think we're going to spend majority of the time on that. Really, when you're moving your stuff to production, you need to have a highly available cluster. That means your masters usually won't be a single replica, but rather multiple ones. And then the etcd database, which is the persistence layer, every object in Kubernetes is getting persisted onto etcd. So that is kind of a critical piece on its own, because if etcd is down, then, well, whatever is running is still going to keep running, but you cannot provision anything new on your cluster. And you're going to lose the state of your cluster, which means the desired capacity of each of your services, and so on and so forth. Any secrets that you had stored. So really, when I kind of started to look into how do I convey the message of how complex it is to run those things at scale, I ran into one of the articles, an interview by one of the CNCF ambassadors, and he really knows a lot about Kubernetes, but just by judging based on what he said, you can tell how complex that is to run at scale, because you have multiple things to consider. Things like, for example, if you want to have a quorum, you need to be resilient to at least one failover of the server, so you need to have a quorum of 3. If you want to be resilient to 2 fails of a master node, then you already have to have a quorum of 5. And that's masters. You can actually replicate those. But what about components like the DNS server, for example? That's only a single replica. So what happens if that goes down? Then you don't have service discovery in your cluster anymore. Not to mention the fact that you have things like controller managers that are like working in active passive mode. That means that whenever one is failing, the rest 5, 4, 3 components that you have are going to start racing towards, hey, I'm going to pick it up instead of the previous one that failed. So this thing is complex to run and manage at scale. That's kind of the bottom line of it. And when we start to kind of talk to customers and understand what they're doing, 2 things popped up. One, we really have a significant amount of customers running Kubernetes on AWS, the majority of workloads actually. And the other one was, they all asked us, or majority of them asked us, to run this thing for them. At least that particular control plane, which is hard to configure, hard to provision, hard to manage, hard to scale. So with Amazon EKS, the first thing that you get when you're building that is a fully managed control plane, which is being built when you're creating an EKS cluster. So on EKS, every cluster actually has its own control plane, which is made of multiple masters and multiple etcd instances that are running across multiple AZs. And what you're getting is a managed AWS endpoint that is basically your master endpoint. So you will point all your worker nodes and all your configuration tools like kubectl to point to that particular endpoint. When it comes to communicating between the workers and the masters, this is kind of a cross-account provisioning, which means the control plane components are being provisioned on our AWS service account, whereas your worker nodes, your EC2 instances that you're bringing in to run the pods, are being provisioned on your VPC and your account. And so the way that they talk to each other is the workers talk to the master through the public endpoint, which is public today. And we also already announced that we have plans to make or have available a private link endpoint, and we're going to do that next year too. And the vice versa, so when the masters need to talk to the workers for commands like kubectl proxy or kubectl logs or kubectl exec, so that's being provisioned by us creating what we call a cross-account ENI. So whenever you are creating a Kubernetes cluster, you need to specify a list of subnets and a VPC in which you will run your workloads in. Now, we are taking those subnets, tagging them, and provisioning cross-account ENIs in each of those subnets so that the masters would be able to talk to them for that particular communication. So that is the way that is being provisioned behind the scenes when you guys are creating your EKS clusters. So I want to shed a bit more light on the networking aspect of how Kubernetes networking runs on Amazon. So first of all, from a pod perspective, when you guys have a bunch of pods on your machine, they need to be able to communicate. Kubernetes is not opinionated as to how you implement your networking, as long as whatever network implementation you have will sustain those three simple rules, which are all the pods need to communicate with each other directly, no NATing involved. All the pods and all the nodes need to be able to talk to each other interchangeably. Again, no NATing involved. And then whatever IP the pod sees itself as should be the same IP that other pods in the system sees it as. As long as your Calico or Flannel or whatever implementation you have and all of those do maintain those, you're all good to go. And so we actually created an AWS VPC CNI plugin. CNI, for those of you who doesn't know, it's Container Network Interface. It's kind of a generic interface that most of the network implementations for Kubernetes basically follow as a guideline to how to implement networking. And so AWS created a specific CNI plugin that uses our VPC as a way to communicate between your pods. So what happens is every time you're spinning up a worker node, there is a CNI plugin that runs as a daemon or as a daemon set inside that node. It contains a component called IPMD or IP Manager, which means that particular manager will maintain a list of ENIs on that node and a list of IP addresses that are associated with them. So for every ENI, we actually provision multiple secondary IP addresses, and Kubernetes will be able to leverage those secondary IP addresses to use for scheduling your pods. So for example, if you have an instance that can bind 4 ENIs based on that instance type, and each of those each of those ENIs can have 8 secondary IP addresses, that's the multiplier of how many pods you can actually run in that node. So that's the kind of max density that you can get for that particular node. And obviously, you can scale that with bringing in more nodes to the cluster. But that's not the end of the story. So that CNI plugin actually makes VPC calls to our VPC endpoints and fetching ENIs and IP addresses as kind of a warm pool to be able to allocate to any running pod. And then any pod that is getting scheduled basically takes one of those specific instance pool ENIs and secondary IP addresses and associates them with the underlying pod. The daemon runs in its own, so it runs in the root file system, and it's connected to the pod namespace through what we call a VF that bridges them and connects them together. So what does that all mean? It means that essentially what you have is you have VPC networking running in your pods. Unlike solutions like Calico or Flannel or any other network implementation for Kubernetes, this is not an overlay network. There is no overhead of running an additional networking layer, but rather just using the standard VPC with all the implications of a VPC. You get like a high performance, low jitter network that you can use with NAT gateways, with route tables. Everything that the VPC offers is now available to you through your Kubernetes workloads. So just to shed some light on how the IP allocation works, or how does your VPC gets allocated to the multiple workloads that we create for you on EKS. So when you're creating a primary VPC, which is to be used for your EKS cluster, you're using a specific primary CIDR range for your VPC. That can be one of the RFC 1918 ranges. And then those ranges will be part of the subnets that you're providing to us on cluster creation, the one that we are tagging and using. So those will be used for pods. As I mentioned earlier, we'll allocate those secondary IPs to pods from that. But we're also going to create the cross-account ENIs and assign those IPs to them too. And then the third thing is, when you're creating Kubernetes services, and we'll talk about Kubernetes services in just a bit, those services has what we call a cluster IP. That is an internal virtual IP created by Kubernetes. And the range that we assign to those internal service IPs is going to be based on whatever you have selected for your VPC, but it's going to be a different one. So what I mean by that is, if you've created any other than 10.0 to your VPC, then we'll allocate 10.100 to your service range for creating the internal IPs. Whereas if you created the 10.0 for your IPs in your VPC, we will not use that for your internal services in order to give you the maximum IP space that you can use or leverage for your pods, but rather use an alternate an alternate IP range, which is 172.20. So in some cases, you will create an EKS cluster and you will see the internal IPs as 10.100. In other cases, based on what you've configured to your VPC, you will see a 172.20. How does that all work? Again, creating the EKS cluster, providing the VPC and the subnets that you want us to use, and then everything else will be created by and provisioned by our EKS control plane. There is a new feature, however, that allows you to extend or further extend the range of IPs that you will use for your pods. So some customers have been asking us to kind of say, hey, we have exhausted the list of IPs that you can use from our CIDR or our primary CIDR range for our VPC, and we would still like to be able to run more IPs because we have more pods than that. So for those, we actually enabled a new feature which allows you to add secondary CIDR ranges of your VPC and allocate those specific ranges to your running pods only, not for your cross-account ENIs, not for your internal IP services, but what you care about, we do deliver, is the ability to assign more IP space to your pods. Now, how does that get provisioned? First, you have to use our latest CNI plugin version, which is 1.2.1 or anything above that. And then what you need to do is you're enabling that feature, and the documentation will state how to enable that feature. Once you did, you need to create something called a custom resource definition. Now, that's a Kubernetes construct, or a CRD. A CRD is a Kubernetes construct that allows you to make specific definitions that can then be made available to your running services and pods. So in this case, we will create a custom resource definition called ENI config. That is basically just a snippet of configuration that says what is the IPs, what are the security groups and the subnets that you want to further allocate to your running pods. And that's going to be configured on a host basis. So for each of your hosts, you're going to be annotating that host with the specific ENI configuration, creating those additional subnets or enabling those additional subnets and additional security groups to be used by the pods that are running on that pod, on that host specifically. Naturally, those subnets would have to be subnets that are in the same AZ as the instance that you are running on, obviously. So just to highlight a few of the other kind of newer functionality that we have enabled on our latest version of the CNI plugin, for those of you who haven't heard. So in addition to the custom network configuration, which I just talked about, we also enabled what we call external SNet. So SNet is a source network address translation. What that means is that we specified earlier that each of your pods is getting its own IP address in your VPC. That's an internal VPC address, which will not allow it to communicate with the outside world with the internet. Now, if your pod is running on a host which runs in a public subnet and needs to communicate with the internet, what we do by default is whenever it makes that request, there is an SNet component that translates, or the CNI plugin translates that internal VPC address to the host's public IP address, which then in turn allows it to communicate with the internet. So that's basically the way it's going to work. And for other use cases, that is not going to be very helpful. For example, if you have a need to connect your pod to an external traffic coming from a separate IP space, which could be a VPN connection or a direct connect, that's not going to work so well for you. So for those kind of use cases, you would put your pods on a host that's running in a private subnet, and you would disable SNet by specifying the external SNet flag. Now, what that means is that external means that you have to now take care of providing an SNet if you wanted that particular node pod to be able to talk to the internet. And that can be in the form of any network address translation service, for example, the AWS managed NAT service or any other netting service that you guys are using. But that's something that you will now have to configure yourself. So this is the basics of how the pod-to-pod communication works, or pod to the outside world. I want to go over one of the very important aspects of running Kubernetes, which is services. So I'm pretty sure most of you know this, but services are kind of an abstraction that allows you to take incoming traffic and actually route that to a bunch of pods that are representing your application or your microservice. Now, there are a number of ways to do that on Kubernetes. So the first one is the cluster IP. And where you're creating a service, you will have to specify what is the service type that you want us to implement. And as you will see, this is kind of a layered architecture, and I'll show that in a second. But the first, most basic mode would be a cluster IP. Remember earlier when we talked about we can allocate specific ranges to our internal services on Kubernetes, that is those internal network ranges that I've talked about. So every time you're creating a Kubernetes service, one of those IPs will get allocated as a cluster IP, which again, a cluster IP is a virtual IP. It's only accessible from within the cluster. You cannot access the cluster IP from outside the cluster, but it's really good if you wanted to communicate between your microservices internally. Now, there is a proxying that takes place whenever you're making a call to the cluster IP. The proxying can be of several types. The most common one being used is IP tables, and that is being managed by a component called kubeproxy. So kubeproxy is a component that sits on each of your nodes and manipulates the rules or the traffic in a way that will actually forward or route that to the right pod. So in IP tables mode, kubeproxy itself is not involved in the request itself, but rather what it does is it manipulates the IP tables on that particular host and making sure that the IP tables rule will actually forward the request that you have hit with that particular node to the right pod that you have. So that is the IP tables mode. There are other modes like user space, in which the kubeproxy itself will take an active participation in forwarding the request. And then there is a newer mode called IPVS, which started to get picked more and more because of its increased efficiency. So those are like different modes of how you can proxy a request from hitting this cluster IP onto your running pods. So that's one option. The other option you have is you can use a node port. A node port basically exposes your service on each of the cluster nodes, regardless of whether it's running the specific pods or not running the specific pods. Each of your cluster nodes will now have a specific port open to each of your node port services. What that means is that there is a certain routing that could take place if, for example, you're hitting a node, but that node does not even have the pod that you're trying to reach. So there will be a redirect and forwarding of that request to the right place using a cluster IP service. So basically, the node ports are all forwarding the request to a cluster IP service, which we talked about earlier, which gets created every time you're creating a node port. So you can look at it like we have an external endpoint on each of our nodes on a specific port. So it's going to be the same port for a specific service on all the nodes that we have. And that request, no matter which node it hit, will get routed to the cluster IP, and from there on the same path that I explained earlier. And one thing I forgot to mention is that cluster IPs are accessible from the outside. So you can actually call the node IP and the specific port, and you will be able to access that service. But it does leave upon you to do kind of the load balancing aspect of hitting the right set of nodes or node as to make your request. So there's no load balancer involved there to kind of be the single endpoint and forward the request to multiple nodes, but rather it leaves upon you the responsibility to choose whoever node you wanted to call for that particular service. So the third mode that we have is a load balancer. That is a mode that's available only on a cloud provider like AWS. And that will, in turn, when you're creating a load balancer service, will cause a creation of a load balancer. In AWS's case, it would be an ELB or an NLB. That would be Elastic Load Balancer or a Network Load Balancer, which is kind of the newer generation. And then that load balancer will forward the requests back to the node ports, the node port service that gets created, which has its own cluster IP too. So you can see how that's all being layered one on top of each other. But obviously, the load balancer can give you the benefit of having that load balancer sustain all the traffic that you can that can come in whatever pace, and kind of be the shock absorber of that traffic, and then offload that to your to the pods that are running behind it. Now, obviously, you also get benefits from the load balancer itself, which are whatever the ELB can offer in terms of encryption, certificates, security. So those things can be provisioned as kind of annotations that you can configure on Kubernetes. So if you go to the Kubernetes documentation, you can actually see a lot of the annotations that you can put on provisioning features for your NLB, or sorry, for your ELB, as to how to make those available on running on AWS. Now, the NLB is a kind of a newer option. It's been made available ever since Kubernetes 1.9, but it's still an alpha feature, so it's not yet kind of endorsed as a recommended production service to use. The way to provision an NLB rather than an ELB is done by a simple annotation. I think the big benefit of that is, one, we will keep adding more and more features into that, which will allow you to use and take advantage of the NLB's advantages over ELB. And then the other thing is that it will support other more refined Kubernetes options. One of such would be the external traffic policy. So basically, external traffic policy allows you to override this forwarding that I talked about earlier that's happening between nodes. It means only the specific node that will get hit by the request will get routed that request. So if you have pods running on that node, good. If you don't have pods running on that node would fail the NLB health check and would get deregistered from the target group that it actually uses to route your requests. So the bottom line of it is that if you're using an NLB, only nodes that are having active pods that belong to that service are part of that game, or part of that backends that NLB can forward traffic to. Now, what that means, though, is that that could lead to an uneven distribution of traffic, because if you have two nodes that have running pods for that service, one has a single pod and the other has 4 pods, The traffic will go 50-50 between those two nodes, but that obviously would lead to an uneven balance between the pods getting the traffic. So a way to kind of override that would be to either use a daemon set to make sure that you only have one pod running for each of your applications on each of your nodes, and then or use anti-affinity rules. That means that two pods of the same type cannot run or cannot coexist on the same node. There is a fourth type that's not being, I think, as well known as the rest of three, which is called external name. External name is actually a service that creates a DNS entry, and it returns a CNAME that will correspond to whatever DNS resolution or whatever DNS name you specified on creating that service. So there is no routing or forwarding or proxying that takes place when it comes to this. It's just a simple DNS CNAME resolution. Now, another construct that customers use to run or to have provisioned incoming traffic onto your Kubernetes cluster is called an ingress. So an ingress is, you can look at it like an entry point to your cluster, which can receive L7 traffic, and then route that traffic and propagate that to the multiple services that you have based on things like host-based or path-based routing. Now, there are multiple implementations of ingresses on Kubernetes on AWS, including Nginx and F5. Zalando has an implementation. There is an implementation that we kind of took ownership on, which is called the ALB Ingress controller. So the ALB Ingress controller is a component that provisions an ALB in order to implement an ingress resource that you guys define. So when you're creating that ingress resource, an ALB gets provisioned. A target group and listeners are getting created for each of those services that you need to route traffic to. And that, in turn, allows you to use things like host-based or path-based routing in order to determine which sort of traffic will route to which of the services. Now, we also enabled a new operation proxying mode, which is called an IP mode, that allows you to not only forward the requests back to the services, but also override the node port mode that I've talked about earlier and go straight to pods. So remember, in Kubernetes, each pod has its own IP address. So those pods can actually be directly configured as the backends in that target group that gets created. And this leads to further efficiency routing your request because you don't need to do that proxying through a node port anymore, but can just go straight to pods. So that's kind of a new feature that the team has developed over the last few weeks. We also made the ALB Ingress controller in its new form. So it's a 1.0 version of it, which means it is now much more stable, much more performant, and also is officially supported by AWS. So if you guys are using ALB controller, Ingress controller, you can actually open support tickets to us, have our guidance and training as how to use it. It's going to be part of our official docs for Kubernetes. And so this is one kind of improved option that we offer for you to implement your Ingress resources. So a recap of what we have so far. So we have a cluster. We have a managed control plane. We have pods that are running in that cluster with multiple services that can have different types and different forms. And then what we now want to do is talk about security, because we want to make sure that pods in the cluster can be accessed in a secured way and can access other services in a secure way too. So when it comes to runtime security, this is kind of a broad topic that I can spend like 2 hours easy just talking about that. So I won't be able to cover all the aspects in this talk. But one thing I wanted to highlight on security, and that's something that a lot of customers I spoke to this year have asked, is like, we want to be able to access other AWS services with our applications because we're part of running on AWS. So we leverage things like DynamoDB, we leverage things like S3 or our EMR or any other AWS service. And we want our pod to have those fine-grained permissions to be able to use that. The same way like you get with ECS or Fargate, we want that to be available for pods on Kubernetes. And previously, or even currently, we don't have any native solution to provide IAM rules for pods. So first I want to go over what we do have today, or what the industry and the community has, which are options that you can use here and today to provide granular permissions using IAM to your running pods. So basically there are 4, I think, projects that kind of stand out in terms of how you can do that. And they all have different characteristics and different trade-offs. Kube2IAM is actually, I think, the oldest one. It's pretty mature. It's being used in production by several companies, including Zalando, Atlassian, and others. One thing about Kube2IAM, though, is that it's running as a daemon set on each of your cluster nodes. And that means that each of your clustered nodes needs to have an assume role permission to assume any role that it needs to, which your pod may require. And that kind of leads to a security issue in which pods that are running before Kube2IAM initializes could actually get underlying access. Now, the way that that works is those solutions, especially Kube2IAM, they proxy every request you make to the EC2 metadata endpoint, and they provide those credentials themselves. So they actually make the request, fetch the credentials, and then hand them off to the pod that needs those credentials. That's a fair way to do that, but there are better ways. So for example, IAM for Kube is running as a specific deployment that's running in a separate node, not the nodes that you guys are running your workers on, but other nodes. So only that particular set of nodes has those assume role permissions. So if some pod in your system managed to breach the container security boundaries, it would still not get any underlying security access to the EC2 metadata API through the assume role that got installed, because there is none. The way that it works is that all the requests are getting routed by an IP tables manipulation to that particular server that runs elsewhere. So only that service is the one that makes the calls to the EC2 metadata. So that kind of reduces significantly the blast radius that you have for IAM for Kube. The KIAM one is taking a different approach too. It actually has agents that are running on each of the nodes, but those are not the ones that are fetching the credentials. So there is a separation between a server that runs only one instance, which is the one that has all the assume role ownerships and is the one that fetches the credentials, and then the agents that are actually only proxying the requests and getting those credentials from that one single server. So again, those solutions take different approaches as to how to mitigate different security issues. There also could be race conditions in those solutions, which leads to, again, in Kube2IAM, that can actually lead to a pod getting underlying access to credentials it doesn't need to. But in other cases, it could just lead to kind of a race in which your pod got scheduled before, for example, KIAM, which means it just doesn't get any access. It will make a request to get the credentials, but there is nobody to answer that yet because it hasn't been initialized. So it will result in I can't fetch credentials for a certain period of time upon initialization. The fourth solution, Kube AWS IAM controller, actually takes an entire different approach to that. That's actually a single instance that only makes a request to fetch the credentials, but makes them available to pods by injecting them as mounted secrets. So that kind of relies on the trait that means that every time a pod is launching, it has to have the mounted secrets available to him before they start running. Which means that by default, every time you have a pod running, you will have that secret available to you, so you will have the credential that you have. So there are no race conditions in that. But there are other trade-offs. So for example, production experience. We have seen significant or at least some production experience with Kube2IAM, and slightly less than that with KIAM, but none, at least not that we have heard, on using IAM for Kube or the Kube AWS IAM controller. So those have not been tested yet at scale and in real production scenarios. One other thing to call out, and that's kind of a benefit for IAM for Kube, it's the only construct that uses the service account as a way to inject the credentials to pods. So when you're annotating your asking for your credentials, in most cases, in most of those solutions, you will get that by annotating the pod with whatever IAM role you want it to have. Whereas with IAM for Kube, you actually annotate that on a service account level. Now, a service account is actually kind of a construct or an abstraction that provides identity to running pods. So you can have multiple pods that are running under the same service account and will enjoy the same credentials being offered. So I think as a design decision, this is a really good one that we like. Now, having said all of that, and by the way, if you guys wanted more details on comparing those solutions, on the top left corner, there's a QR code that if you scan will lead you to a kind of an article that will give you a table of comparison that shows the different trade-offs and design decisions between those four. Now, Kubernetes itself is working on providing native support for the API server for what we call OIDC, or OpenID Connect. Now, we have our own proposal on how to provide native IAM support for pods, and we're going to implement that next year. And we would love to rely upon having the ability to have OIDC support on the API server as a construct for us to use on that solution. So there will be more to come on that going forward. But for now, those four solutions are available to you, and you can choose whatever of them seems more right for your use case based on those criteria that I defined. One more thing I wanted to kind of highlight in terms of the data plane. So we talked a lot about the control plane. We talked about how you can configure networking, how you can configure security, monitoring, logging, and tracing. So for monitoring, I won't be able to cover that much, but we have a lot of tools that are being widely used in the Kubernetes community. And I think the two that stand out are Prometheus and Grafana. So those tools should be available for you to use with EKS too. If you guys, or for those of you who doesn't know, EKS is a 100% Kubernetes upstream conformance service, which means we actually go through the Kubernetes official conformance testing on every version that we support. We have done that with 1.9 and 1.10, and very soon with 1.11. What that means is you should be able to run pretty much any tool from the ecosystem that supports monitoring, logging, security, should be able to run on EKS. So Prometheus and Grafana are two that would kind of stand out. If I had the time to show you how to provision that, I would, but I think there may be other sessions this week that kind of will maybe dive deeper into that. What I wanted to show is about logging. I've had a few customers recently that asked, like, what is your recommended approach on making those Kubernetes logs, those application logs that we have running on multiple pods available for us with EKS and on AWS. So again, we're not opinionated as to which solution you guys want to use. You can use commercial solutions like Splunk or open source solutions. One pattern, though, that kind of has stood out as a lot of customers are using that is the EFK stack. EFK stands for Elasticsearch, FluentD, and Kibana. So FluentD is actually a very widely known and popular component for collecting your data. It has a lot of plugins that you can use to stream that data straight to whatever centralized mechanism you want to have, including CloudWatch logs, Elasticsearch, and many others. Elasticsearch itself is a very commonly used and distributed analytics engine that you can use to kind of aggregate all of your logs and then analyze them. And then Kibana is a really good way to visualize all of that. So a typical workflow on your EKS cluster or on your Kubernetes cluster would be having the FluentD run as a daemon set on each of your nodes, and then sending, and here we have two options. One option is you could use CloudWatch logs, and FluentD does have a CloudWatch logs plugin, so you can forward a request to CloudWatch logs, and then CloudWatch logs by itself have a subscription that allows you to forward those logs straight to a managed Elasticsearch service if you're running one on AWS. So if you're running a managed Elasticsearch service, that could be like a good way for you to provision that, assuming that you wanted the benefits of getting CloudWatch logs in the middle in terms of being able to do some filtering, searches, before you kind of make the final transition to Elasticsearch. So it's kind of like the first line of filtering that you get when when you're actually provisioning that flow of logs. Another way would be to just avoid CloudWatch logs and just use the Fluentd connector plugin to Elasticsearch itself, in which you can use any Elasticsearch cluster that you want and have that be visualized with Kibana, whether it's a managed service or elsewhere. So these are just a few of the related breakouts that we have this week that could provide some further information. From all of these, I would actually call out the one on Friday. That's a deep dive on Amazon EKS. There has been a session yesterday, but for those of you who have not attended that and you want to get that, there is another session that's happening on Friday. It will basically cover some of the other aspects of EKS, like how do you provision your worker nodes, how do you provision your AMIs, and other things as well as kind of touch upon the new items that we have released recently. So with that, I want to hand it over to Carl, and thank you so much, and enjoy the rest of the presentation.
Thanks, Yaniv. Let's see. It's not working. There we go. Oh, too many slides. So I'm going to take a step up a little bit and actually give like our perspective on our transition to Kubernetes and EKS. And I'm going to specifically talk a little bit about vanilla Kubernetes versus on EC2 or wherever versus EKS and our decisions around that. So I'll take a step back to kind of give some context and history on Snap as a company to make the rest of my talk make sense. So we were actually founded in 2011, and really starting from 2012 on, we had really rapid growth in employees and software engineers. And so a lot of the problems that I'll talk about that we went through are really organizational problems or like fast growth problems. So for customers that are going through similar transitions, some of that might be relevant. So when we think about kind of, I guess, any technical decision, but certainly infrastructure decisions, we generally start with first principles, and each particular example, we make different trade-offs. But these are, at a high level, probably some of the top 5 things that we think about for any project. I mentioned our rapid growth. There was a time where flexibility was the most important thing all the time, even sacrificing that over security in some situations, right? We wanted development teams to be able to move as quickly as possible, not have to worry about provisioning infrastructure, just building on top of what we already had. Even today, that's a really important goal for us. We've actually gone through some organizational transitions where instead of having a bunch of independent teams that work separately, we kind of have some central platform teams that provide higher level services to internal development teams. Right now, they're probably about maybe a fifth or so of our software engineers work on teams like that. That supports both infrastructure as well as mobile, which is actually where most of our energy goes into. Security, I kind of said it sometimes wasn't important. Well, these days, it's probably always one of the most important concerns. And I think we look at products like Kubernetes and EKS with the security lens, right? We were initially a little worried about using containers versus fully virtualized instances. But obviously, like a lot of what Yaniv was talking about, like full IAM support for pods would be an enormous thing that we would love to start using once it comes out. A little anecdote. So I started at Snap, actually came from AWS in like summer 2014, and my style is to just observe for a while and see what the land looks like, and then make recommendations. So about 2 weeks in, I went to my boss and I said, availability is the most important thing we have to work on. We just had 5 2-minute outages in the past week that were totally avoidable. And this was 2014. He said, yeah, I agree it's important, but on my list, it's probably number 20. And the reason it was number 20 is there were so many product changes, so many things we wanted to do with the app itself that were more important, that wasn't initially that important. But over the years, our expectations from our users have only gone up. And performance has, I think, always been important to us. But performance and availability are becoming almost as important as security in our perspective. As with employee growth comes infrastructure cost growth as well. Initially, efficient infrastructure wasn't high on our list, but as the absolute amount of money we spend on infrastructure has grown, that's become more and more important. We actually have several teams now dedicated to measuring and thinking about cost reduction. Kubernetes is a big part of that for us. Like I'll talk about some of our specific transitions, but obviously getting the most out of an instance, scheduling kind of different kinds of tasks on instances is a good way to improve efficiency. And finally, we have a lot of younger engineers that haven't had to kind of operate their own infrastructure. So a lot of our teams are really looking for simple operational solutions. And for teams like that where operational insight isn't going to give them much useful information about how their service works, we're happy to provide kind of higher level operational paradigms for them. Okay, so here's the history lesson. So I'll talk a little bit about the way things were a couple years ago, and then I'll transition to how we're changing, we've changed a lot and we'll continue to change things. So I think a lot of small companies that grow really rapidly take this approach. We operated with most of our infrastructure in a single large monolithic application, actually a couple large monolithic applications. And I mean monolithic, I guess, in two senses. Monolithic in a runtime sense, like literally we used to have an application that was like a 600 megabyte WAR, and with hundreds of APIs and actually contained inside that WAR. But I also mean from a code-based perspective. And obviously, for most companies that continue to grow, this becomes an impediment after a certain amount of time. We were starting to see problems a couple years ago where projects, most of our projects involve a mobile work as well as infrastructure work. It should pretty much never be the case that the infrastructure work is the long pole in any projects, because mobile engineering, if people haven't worked on it, is much harder than infrastructure. It's much more like traditional shrink wrap software, where if you make a mistake, you're stuck with it for a long period of time. But we were starting to see projects where that was not true. The infrastructure was actually the long pole. So that was a good signal for us to start thinking about how to change from a large monolith. Secondly, as we grew, we obviously didn't grow by just single teams getting larger and larger. We subdivided responsibility and ownership. That created a secondary problem, which was often teams had to collaborate in order to ship something. And we evolved sort of defense mechanisms over the years where, because a monolith, it has a lot of strengths, but one of the big weaknesses is if one person makes a mistake, it can affect everyone. We evolved kind of a set of processes around kind of gatekeeping into code changes into that monolith for things that were deemed high risk or potentially large in scope. And that was a good strategy, but it created a lot of tension, right? No one wants to be on the team whose job it is to police what other development teams are doing. Symmetrically, no one wants to kind of ask for permission to do something. We'd rather just have teams work as independently as possible. And maybe another element to that is we started having geographically distributed teams that had sort of different cultures and different histories about how they approach engineering, and they were probably some of the most vocal teams in terms of not wanting to ask for permission to do certain things. And finally, in terms of problems, although it was possible and we had a fair amount of individual services that were regionalized, it wasn't possible to make coherent application-wide regionalization decisions. Everything was kind of siloed. And for us, during this period, 2015, 2016 was really when user growth at Snapchat was really at the highest growth rate ever. And that was primarily occurring outside of the United States. Most of our infrastructure was actually in the US at that point. So regionalization was a big thing we knew we needed to work on. Rather than take our big monolithic thing, try to regionalize that, we decided to start to decompose it and regionalize the component parts. And obviously, performance is the #1 reason why we would regionalize. Obviously, availability is the secondary reason. But for us, it's really about delivering media and delivering metadata to clients as quickly as possible. So this slide's probably a little boring. I mean, obviously, SOA is a good solution to the 5 or 6 problems I just identified. It really does solve a lot of those things, or at least help dramatically with a lot of those things. Letting a team own a set of services that do one thing, but do that one thing very well, you're just going to end up with better software, more efficient software that has fewer bugs. Security was a big driver, though. We had built a lot of infrastructure around the monolithic application to compartmentalize and not allow any random developer to get access to things. But that created some tension. It basically meant that when you did need access to certain things, it was harder to get access. Obviously, a set of services that have different databases and different sets of access controls is a much cleaner way to do that. And again, SOA, I'm a big fan of having your organization, org structure map closely to what your application SOA structure looks like. It's probably not always right to have it perfectly match. But we thought that moving to SOA would give us a better growth trajectory when it came to launching new services or launching new products. So that's kind of the obvious slide. I think the question then is what do we do? What's the actual path from big millions of lines of code monolithic application to where we want to go? Containers, I think, were the obvious solution. In fact, it solved a different problem we had. It used to be impossible to even run and test our application on your laptop because the 600 megabyte WAR is too big, and plus it required all these dependent services that we didn't have mocked out. Containers help with that too. But they're not even probably close to half the battle for a big set of services like ours, right? How are you going to run those containers? How are you going to deploy them? How are you going to manage them in an ongoing basis in an efficient way is the real question. So solutions like Kubernetes were, I think, obvious. Like, it was sort of lucky, I think, for us in a sense that Kubernetes started to get traction around the time when we were thinking about making this transition. We actually invested a lot prior to the transition to Kubernetes in a framework that was internal to Snapchat that solved a lot of these same problems. And actually, a lot of that stuff that we built then has actually been carried on and is run as part of our Kubernetes clusters. But when we saw, like, there's so much momentum behind Kubernetes, we wanted to kind of switch over to that solution because we saw it as the future. But we're presented with this question, like, should we run it ourselves on EC2? Should we run it ourselves on other cloud providers? Or should we use the managed service? Philosophically, if I went back to my first slide, we definitely have, we prefer to use a managed solution when it's only a little bit more expensive and it provides some significant value. Or it replaces work that we could do ourselves, but that is not going to be value add for us. So to us, like, a lot of the problems that Kubernetes solves fit that definition, right? Yes, we could figure out our own way to, like, carve up instances into smaller units and manage where pods are deployed or where containers are deployed. But that's a solved problem, right? Or we could come up with our own solution about how to react to data center failure, zone failure, and scale up in another zone. Again, that's a problem that's going to be solved by Kubernetes. But the question remains, like, EKS versus vanilla Kubernetes. ALB Ingress controller, I think that Yaniv mentioned, is a good example of what we think is going to continue to happen in the ecosystem. I think Amazon will likely continue to launch integrations with services that we want to use. And load balancing, structured storage, blob storage, these are services that we generally philosophically want to use the cloud provider offered version. They're really hard to operate. It's super hard to not lose data in those systems. And so we expect to see kind of this leapfrog effect where services or better integrations with AWS services are launched first in the managed products like EKS and ECS, and then do eventually make their way back into vanilla Kubernetes. But we want access to those things as soon as possible. Like, load balancing is a good example. We were, I'll get into some of the real production workloads that we have running, but we were running individual, like, Kubernetes-style load balancers on individual services or nodes just to start out. And we knew that was not going to be a viable solution when we launched products to production. Luckily, a lot of the load balancing features did launch in time for us to actually use them. One other point on that, we actually don't think that the slight portability differences between, it's not really working. OK, here we go. The slight portability, less portability that you would have by building on top of EKS is that big of a deal. At the end of the day, I think there's going to be more inertia in switching away from something like DynamoDB to a different solution than there is when reconfiguring your containers to run in some different version of EKS. So where are we right now and where are we going? So we currently have about 6 services in production. We're going to see actually something like 14 or so by end of year. So there's actually a lot of growth happening in the last month of the year, if everything goes right. Next year, we hope to have about 50 services, again, if teams kind of meet their commitments that they made. And the end state, we have something like 1,600 APIs that our mobile application talks to in the old monolith. We've migrated maybe, I'm guessing here, 70 to 80 already. We think we'll end up with several, not each of those APIs operate on different data, right? So our general segmentation strategy is, if a bunch of APIs operate on the same data, those should probably be in the same ultimate service. But we expect to have several hundred services, mostly running on EKS, in several more years. We don't have a detailed timeline, so I'm kind of being a little vague there. But a lot of things we're going to be doing over next year and this year is focusing on making decisions about regionalization. We want to provide, I think it's hard, right? Like, most teams would want to over-provision to the point where their service would always be available in the face of any infrastructure failure. And from a business perspective, that's actually not the right thing to do, right? Some services really do. We have a concept of service tiering internally. And so for high availability services that really need to be up in all cases, that probably is the right strategy. But for example, for a batch processing workload that you could just delay for an hour or two, if Amazon did have a zone down, maybe that's not the best strategy. So we want to provide some guidance and recommendations and tooling for teams to use to make these decisions internally at Snap. So a few more stats. We currently have about 7,500 cores running various. We think we have a couple EKS clusters right now. If you sum up all the average transaction rates per second for those services, it's about 250,000 QPS. So we are using NLB and ALB for a lot of these services. One thing that's, I think, worth mentioning from our experience so far is we have ended up with relatively large instances with lots of pods packed onto them. And that's worked out to be the most cost-effective way for us to to run things. I think the most interesting thing is with Kubernetes and EKS, this is a decision that one team or one person in your company can make who's responsible for optimizing the clusters, right? So in fact, the development teams that run on those clusters don't even need to know necessarily that we're making a change to which instances type we're using. A good example of that is actually C5 and M5 instances, which we found to be significantly more performant if you sort of measure it by cost. And we were able to replace a bunch of the nodes pretty easily. Actually, that was a case of using ECS by just doing that under the covers without the service owner really being involved. So I'll take, in the last couple minutes, take a step up the stack a little bit and talk a little bit about what we're doing at the application layer. So I mentioned earlier we had developed a bunch of stuff to make it easy to deploy services to physical infrastructure at Snap. And so we were able to take a lot of our custom logging agents, custom metric agents, and just carry those over to Kubernetes. Obviously, there was a little bit of work to repackage those, but it was a lot easier than doing it all over again. We're using Envoy for sort of application layer proxying, I think for a couple of reasons. We actually have a fair amount of languages in use in production. And so a proxy like Envoy allows us to have very consistent rules and guidelines around how RPCs should be made between services without having to implement libraries in each language. But we also want to have kind of governance around service calls. So I mentioned tiering. We don't yet really have these rules in place because we only have 6 services in EKS. But we do want to create rules that actually prohibit or maybe more like whitelist certain API calls from service to service so that we can kind of avoid people from taking unplanned dependencies or maybe dependencies on a layer that is above the tiering that your application is in. Envoy is going to allow us to do that. I think another cool thing about EKS is Envoy, I think it'll probably be around for a long time. Seems like there's a lot of momentum behind it as well. If that turns out to not be the solution that people are moving towards in a couple of years, it should be relatively easy to swap that out. I'd imagine any future thing would probably even provide some kind of backwards compatibility. So how has this helped the company? So I mentioned earlier just like packing more pods on instances has already saved us a lot of money, which is great. Snapchat has a really simple business. Like all of our costs are basically infrastructure and people. And so people are not really an elastic cost in the same way that infrastructure is. So this has really been a big boon for the actual business. Secondly, Envoy is a good example, but I think we'll see this continue to be an advantage, right? Kubernetes, it's just easy. There's so much momentum behind it. There's so many different products that are being built and integrated with it that when someone has a cool idea and wants to use the next thing, it should be relatively easy to integrate that to a given service. Once that team likes it, it's also relatively easy to integrate it with our entire set of services. We are moving or really implementing a model that's kind of like, we hope, one big cluster per region. One big multi-tenant cluster per region. And again, the main reason for that is efficiency. We can probably spend less money if we're using the same infrastructure. There are a couple examples where we might not do that for security reasons or kind of risk aversion reasons. But for the bulk of what we're doing, that's our plan. And we've already seen actually significant performance improvements. We had teams running Kubernetes themselves on EC2, and they would port their application, really there's very little work to do, over to EKS, and they saw immediate performance improvements. A lot of that's probably like kernel tuning and things that we could have figured out ourselves, but the point is it's kind of better for Amazon, or to at least start with the baseline of what Amazon thinks is a good configuration. And to give a sense, we already have 10 teams, so we have 6 production services, but actually 10 teams already using EKS at Snap, so some of those obviously haven't launched yet, but they're some of the 14 we expect. So our next steps are mostly maybe not so interesting for this audience, but 1,600 APIs to migrate, each of which does require some amount of testing and porting, is a lot of work. So that's what we're going to be spending the next couple of years doing. But again, as I mentioned earlier, we want to come up with a couple of kind of canned strategies around how to regionalize applications and give that to our internal team so they can kind of pick and choose what they think is the right thing to do. OK, I think that's it. So a reminder, fill out your survey or Yaniv will kill me. What's that slide? But we'll actually be available for a few questions over here if people have it. We ran out of time, but thank you, everyone.